part where you also have to consider the ions, negative ions, because in the equations for that alpha and beta, which we had already done or seen, we had considered only positive ions, X plus, like that. So here, as you all know that in the lower ionosphere, lot of negative ions are present, negative ions. So along with electrons, you have negative ions. So the total negative charge increases. It is not only the electron plus positive ions, which is normally in the upper ionosphere. Here you have negative ions plus electrons together, a negatively charged.
It will connection sir,
Yes.
hello sir. অকমান ৰবচোন দে আমাৰ ইয়াৰ নেটৱৰ্কটো বেয়া নেকি আপোনাৰ প্ৰেজেন্টেশনটো মানে মোৰ ল্যাপটপত ওলাইছে কিন্তু আমি যে ডিসপ্লে কৰি থৈছো যে হেতু ওলোৱা নাই ইয়াতে স্লো
Possibility of electrons combining with positively charged atoms, okay? But here, because the negative ions are also present, so negative ions can also combine with positive ions. Electrons combining with positive ions, that is a possibility. But now another possibility is that negative ions also combine or can also combine with positive ions, okay? So you have two recombination coefficients. Instead of what we discussed in our last class, that alpha is the recombination coefficient. Recombination means it combines, okay? But here, the recombination can be two ways. Two ways means two types. One is electron recombining with a positive ion, and the other a negative ion recombining with a positive ion. So you have two alphas. Instead of one alpha, you have two alphas. And so you can see here that the equation number is 18. Q is equal to the production is equal to alpha E. Alpha E means recombination of electrons. Ne is the total number of electrons, N plus total number of ions, plus alpha I is for ions, the recombination coefficient for ions, and N minus and N plus. N minus and N plus is the positive and negative ions combining together, okay? So when the ratio between these positive and negative ions may also combine, that is what the second term in this equation shows. Now, the ratio between negative ion and electron concentration, because both are negative, electrons are negative ions are also negative, so you can have a, because their numbers may not be equal, so you can have a ratio, and that is normally written as lambda. Lambda is equal to Ne divided by N minus, that is the number of negative ions. So N plus is equal to 1 plus lambda Ne. Therefore, your Q becomes, instead of only one alpha, your Q becomes 1 plus lambda into alpha E plus lambda alpha I Ne square. Earlier also, what we have shown or seen, we will go back to that discussion again. Here, Q was alpha N square. Alpha N square. Alpha is the recombination coefficient, and N is the number of ions or electrons, whatever, ions. But here, because you have both ions and electrons negatively charged, therefore the equation is modified, and you can get 1 plus lambda. Lambda is the ratio of the electron number concentration to the negative ion concentration, And alpha E, alpha I, already we have defined the recombination coefficient for electrons, recombination coefficient for ions, Ne square. Ne is the number of electrons, squared. Okay, that means it is not linear. Your production in this case, if alpha n square, so it is not linear. Okay, but here if alpha lambda alpha I, lambda is that ratio alpha I is very, very small compared to alpha E. Alpha is the recombination coefficient. So alpha is the recombination coefficient for electrons, and alpha I is the recombination coefficient for ions. Now, if that is very small, alpha I is very small compared to alpha E, then your equation becomes equal to 1 plus lambda, Q is equal to 1 plus lambda alpha E Ne square. You can neglect that lambda alpha I. Lambda is already the ratio, it is a small value. So alpha I, lambda into alpha I, we can neglect. And because we will be assuming that a number of negative ions, though they are present, will be more compared to the number of electrons. You can keep that in mind. The number of electrons produced will always be more than the number of negative ions. Negative ions are present, fine, but they are present in less number. And therefore, we can, in this particular equation, assume that the term lambda alpha I is nearly equal to 0, and therefore we can neglect, and therefore Q becomes 1 plus lambda alpha E Ne square. Okay? So Q is not alpha Ne square. Q is not alpha Ne square, as we had seen in our earlier discussion. So it is 1 plus lambda into alpha E Ne. Alpha E is for the recombination coefficient for electrons, and Ne is the number of electrons. And that is equal to the total number of ions. So in the presence of negative ions, the equilibrium electron density is still proportional to the square root of the production rate, but its magnitude has changed. The term 1 plus lambda, this term in equation 19, 1 plus lambda into, within bracket, alpha E plus lambda alpha I is often called the effective recombination coefficient. In discussing, or while discussing the Chapman function or Chapman deduction, we have seen that that alpha is the recombination coefficient, and it is Q is directly equal to alpha N squared. N is the number of ions or electrons. Now it has been modified. It has been modified that alpha is now a modified alpha, and therefore it is 1 plus lambda alpha E plus lambda alpha I, and therefore it is not the recombination coefficient, but it is the effective recombination coefficient. Effective recombination coefficient. Why effective? Because it takes into account the number of negative ions also present in the ionosphere. Earlier in that equation, if I write Q is equal to alpha N squared, then I neglect the number of negative ions present, or that particular recombination process we neglect. Okay. Now, again, if we talk about that beta, if you remember, the beta is directly M plus E is equal, becomes M minus. That means the electron attaches with a positive, a neutral atom, and makes the neutral atom negative. Okay. Here it is M plus E. Earlier we have seen it is X plus E is equal to X minus. So this beta is the attachment coefficient. Alpha is your recombination coefficient. Modified alpha is your effective recombination coefficient, and beta is your attachment coefficient. Beta is attached. The electron is attached to a neutral species. So making it negative, making it negative. So then we go to that alpha Chapman again. Okay. Okay. Now, this up to this we have discussed that when your alpha Chapman and beta Chapman gives rise to two separate layers because of their the process involved itself. As now also we have seen the alpha q is equal to alpha n square, beta is q is equal to, for beta it is simply beta n. So the processes are different. The two processes are different, and also we have seen or discussed that that beta is a in the lower atmosphere. In the lower atmosphere, beta is very fast. Beta is very fast. So attachment takes place quickly, and then your second the recombination reactions take over. Recombination reactions take over. So lower in the atmosphere, your or ionosphere, because alpha and we are talking about alpha and beta. So let us okay. If you can see this figure, that figure 6, forget about figure 5. Figure 5 is for production at different initial, which different initial energies. If you can see the electron production or ion production will be maximum for the maximum energetic particle. That here it is 1000 MeV. Then it is there. It is reducing, and then this figure. If I look at this figure 5, if my cursor is showing you or you are seeing the cursor, then you can see this 1000. The initial energies are given in MeV. That means the solar radiations, it is 1000 MeV. If the solar radiation is 1000 MeV strong, it is the flux is 1 proton per centimeter square per second per steradian. Okay. Now, if it is 1000 strong, 1000 units strong, then it can ionize to about 20 kilometers or so. At least it can come. It can come. It won't be able to ionize till 20 kilometers, but 40, 50 kilometers or 60 kilometers it can come. And if the energy is less, the incoming solar radiation's energy is less, then you can see for 300 MeV, it also starts somewhere here near the lower atmosphere. Then if it is 30 kilometer like that, and it is going up. It is going up for different values of initial ionizing radiation. Strength of the initial ionizing radiation. How much strong the initial radiations are. If you look at this figure, this curve is for the highly energetic particles. Then it goes up, and accordingly, the height up to which the solar radiations can come down and ionize will also increase. From here to say it is 30 kilometer, from here it is going up to 90 kilometer and like that. So your ionizing particles which are, ionizing radiations which are of different strength can have ionization at different altitudes. If it is strong, that is what the physical process or physically we can think about also. If the ionizing radiations coming from the top is strong, it will come as far, means it will come deeper. If it is weak, it will not be able to come deep into the atmosphere. It is like that, okay? So now this is actually somewhere written somewhere and then taken a picture kind of thing. So here, if I look at these figures, this is the ratio of this. Q is equal to alpha n square, Q is equal to beta n. That means this is alpha Chapman, this is beta Chapman. Okay, so if your ratio alpha Chapman and beta Chapman is around that transition height, this H naught is this transition height, then the production function d and dt will be like this. Okay, but if it is less than somewhere here, if it is less, then it will continue to increase. It will continue to increase. That means if your transition height is at a lower height compared to this compared to your H naught, that is the maximum height of ionization, then it will continue to increase. So here you can see this is H naught. H naught is your maximum production when the sun is overhead. When the sun is overhead, and here we can see an F1 layer. You can see it is kind of a some parabolic shape is there, and then these two dash curves are for alpha Chapman and beta Chapman, and it is going, transition height is somewhere above that H naught, and therefore we are getting F1. But if it is below H naught, you do not get that F. It will continue to increase. That is according to Chapman's theory. Okay. So let me again go back to our. So that is what I have told you. If in the actual ionosphere there is a transition from situation depicted in equation 29 here. 29 is this alpha n square or even 30. So what happens? As I have shown in that figure 6D at height hd. 6E shows the resulting electron distribution when hd is greater than h naught. That is the peak electron concentration at h naught. It is the F1 peak. Okay. So similarly, you have for different values of ht, that if the transition height is less than h naught, there is no peak. This we have to keep in mind. If the transition height between alpha and beta for some reason is below h naught, that means if I consider h naught to be 300 kilometer and the transition height happens below 300 kilometer, then you won't get F1 layer. You won't get an F1 layer. Okay. So in either condition of photochemical equilibrium discussed above, were to remain appropriate, the electron concentration increase indefinitely. Okay. But that is not the actual situation. The terrestrial ionosphere, as we all know, has different layers. Tendency is to separate into different layers. This is the figure. Again. Okay. So this figure, you are very much familiar with this figure. You can see these are different heights, the electron density at different heights. This figure is also in Hargreaves' book. You can see that Hargreaves' book. And if you plot plot the values from any ionogram, we have our own ionograms in the lab. You can go there, ask your say Kolita sir or anybody to give you an ionogram and then reduce. Earlier we had experiments to do. Oh, I wanted to ask one question to Vinita. Will they be doing some practicals also, or they are not doing any practical? Hello?
Oh, sir. Practicals মানে এবাৰ অকল 4 জনহে ষ্টুডেণ্ট সেইকাৰণে practicals নাই তাৰপিছতে কিন্তু সেই আইনোগ্ৰামৰ কাম এজনে কৰে চন্দ্ৰনেলে প্ৰজেক্টে কৰিছে চন্দ্ৰনেলে দেখুৱাব প্ৰেজেন্টেচন এইবোৰ কৰিবলৈ আছে নিজৰ প্ৰজেক্টৰ কৰোঁতে তেনেকৈ হ'ব আৰু কিছুমান বস্তু মানে এনেকৈ কোৰ্চতে দেখুৱাই দিছোঁ যিবোৰ প্ৰেক্টিকেল কৰোঁ মানে
আচ্ছা সেই আগতে প্ৰেক্টিকেলো কৰিলে ইহঁতে টিচি কৰে বা হেৰি কৰে
না থাকে বেছি ষ্টুডেন্ট হলে প্ৰেক্টিকেল দিবই লগিয়া হয় কিন্তু 4 জন হোৱাৰ কাৰণে এটা প্ৰজেক্টে কৰিছে আৰু
মানে that is good. But okay, the others can also ask Sonderlin how to reduce the ionogram or how to see what is the F layer, E1 layer or E2 layer kind of thing. তেওঁ সুধি ল'ব পাৰে বা কেইজনে চাই ল'ব পাৰে আমাৰ একচুৱেল আইনোগ্ৰামৰ পৰা বা প্ৰেজেন্টেশ্যন যেতিয়া দিব তেতিয়া it will be clear to them. Okay, thank you. So what we see is E layer. D is somewhere here, and they assume that there is some C layer also. So D was found to be present with from measurements using rockets only. Ionosons cannot detect a D layer. Then you have E. E is the first layer, as we have said earlier also, that Brett and Touvet, and simultaneously, theoretically, or from that antenna experiments of, they could find that there could be a layer around 100 degree or so, 100 kilometer or so. So they termed it as the E layer, assuming that there will be some layers below and some layers above. So they call that an E layer, and also because it is conducting so electric layer. A layer which has some electric conducting property and therefore E, and otherwise also from the point of view of nomenclature also, E was appropriate at that time. Okay, then F1 and F2, E, F1, F2. But at night what happens, you will see only E and F. F1 normally disappears. F1 normally disappears at night. Okay? So there must be some reason for that. There must be some reason for that F1 to disappear. That F1 to disappear, there must be some reason for that. And while discussing the different layers, we'll come to that, why F1 disappears at night and why D is not detectable using an ionoson. Now, as we can see, any layer that those E, F, and all those layers are characterized by particularly two parameters. One is the critical frequency, the other is the height. Other is the height. Height means not the actual height from the ground, but half height. Half height is your, in this figure, I think this is visible to you, FOF2 and HMF2. These are all very clearly explained in Hargreaves' book also, but for that you will have to go to the first chapter itself. Hargreaves' book, that first chapter, in its beginning of the Hargreaves' book itself, he has shown how the radio propagation takes place in an ionized atmosphere, those equations, how the refractive index varies with square root of electron density. So more electron density means less refractive index or lower refractive index, okay? So that is the reason why the radio waves from ground, if it is projected vertically, will come back from different heights. Total internal reflection, I had talked about that also. The total internal reflection, the refractive index changes continuously with height because the density is changing. So more maximum height means minimum refractive index. Minimum means not zero, minimum refractive index. And therefore, the refractive index decreases from a maximum at the ionosphere. If we consider the bottom of the ionosphere to be a neutral atmosphere, so refractive index is 1. Neutral atmosphere, refractive index is 1. So from there, if you continuously increase in height, if the radio wave goes up, it will encounter regions of higher and higher electron density, as you can see. The radio wave going from here will encounter this region of higher electron density. This is E. And some frequency, if it is equal to that, if the radio frequency is equal to the critical frequency means the frequency which is sufficient to reflect it back towards the transmitter. That means towards Earth. So this is total internal reflection. You know the principle, so well known. So here, if the radio frequency, this is plasma frequency, if the radio frequency is equal to the critical frequency of the E layer, till then it will come back. That means say 5 megahertz. Say 5 megahertz is the critical frequency of your E layer on that particular day or on that in that particular sequence of events or recordings. Then what happens if you have a transmitter which is transmitting at 5 megahertz? Then till 5 megahertz, if it is transmitting at 4 megahertz, 3 megahertz, all these will come back, reflected from this because they cannot penetrate. But if it increases 5 megahertz, then it will pass. It will penetrate that layer and go up. So that way you get the critical frequency of the F1 layer, you get a critical frequency of the F2 layer. Beyond that, normally it is not there, but some people now with very sophisticated ionosons have seen another layer above F2, and that is people try to, some people have called it F3, some people are trying to call it a Z layer. It is not a common phenomena. It is sometimes seen over the equator. Z layer is above the F2. Above the F2, it is a kind of a transient phenomena. Sometimes it occurs, but people have seen, many instruments have now confirmed that there can be another layer above F2. So you can term it as F3 somewhere here, somewhere here. You can term it as F3, or you can, because it is F, so you can have a Z layer. You can also have a Z layer, like F1, which is not always present, but F1 normally daytime you will normally get an F1, but this Z is not something that you will see every day or everywhere. It is seen over near the equator, and with very strong, very kind of good instruments, or you can say with high resolution instruments, and those kind of things are there. So people have seen around the equator Z layers also, but that is not the point for discussion. But I want you to keep in mind that F2 is not the limit. F2 is not the limit. There could be a layer of thick plasma above F2 also. So that is Z. Now, this half thickness is, you fit a parabolic curve. You fit a parabolic curve or to this variation. It normally it appears to be similar to a parabola. May not be always true, but there will be it will more fit a parabola or parabolic curve. So half width means this from here to here and from here to here. So this term is YMF2. Sorry. Your half width. This is called half width. HMF2. HM, who is doing that experiment or project with ionograms, he should be already knowing. HM means height of this F2 layer, height of maximum height of the F2 layer. Okay, so this F2 layer is not at this point. It is this whole layer from here to here, or from here. It starts from where F1 gives away to F2. So we can say your F2 starts from here and goes like this. Okay, all this is F2. It is not that it is only this point. Similarly, F1 also, or E also. It is not that it is at this point only. It has a layer. It has a layer, or has a number of electrons and ions present over a range of altitudes. E layer is normally about 20, 30, or 40 kilometers thick, but F1 can be 100 kilometers thick, between 50 to 100 kilometers, and F2 can be thick, say 200 kilometer, 300 kilometer, 400 kilometer, 500 kilometer. You do not know exactly how high it can go. So this is half thickness. Half thickness means you feed the parabola, and half of it, half distance from the point of maximum is your half thickness. Okay. Similarly, here also, E layer also, you can get HME, maximum of E ionization. And this part you can call it. It is written here. If you see the writing here, this is EF valley. If this is clear, then you see this is EF valley, this one. Okay, this is F1, this is E. So total, if I consider the total ionization, so it is drawn like this. But somewhere you start from here. This is H naught, and from here you go up, and then this is this. Okay. So we have the E layer, and we have the F1 layer, we have the F2 layer. normally measurable with an ionoson. That means ionoson means an instrument which has a transmitter with which you can send pulses, not at fixed frequency, but continuously varying frequency from, say, 1 megahertz to 20 megahertz kind of thing, or 1 megahertz to 10 megahertz. And then it will get reflected at the critical frequencies of E layer, F1 layer, F2 layer, like that. At night, it will have only E and F. It will have only 2 layers. Normally, at night, it will have only 2 layers. These are normal variations. Okay. So, ionospheric layers, how do they form? This I have already explained, this critical frequency. Critical frequency is your proportional to square root of n. That is what I have said. Critical frequency is proportional to square root of n. If you go to the Radcliffe's book, or even in Hargreaves' book, is that first chapter, it is given that equation for the refractive index. Equation for refractive index mu is equal to square root of 1 minus 1 by n square kind of thing. So that n, any the number of electrons or number of ions equal. So if any increases, that is because the refractive index is 1 minus square root of 1 minus 1 by any kind of thing. So what happens? Your 1 is your refractive index at the bottom. From there, as NE is more than 1, you will have a that 1, this is minus, so that 1 by NE square, 1 by NE square, it will be a kind of a fraction, a small value initially. So 1 will reduce by a small value initially, and then as NE square increases and increases, your refractive index will also become less and less. You look at that equation from Hargreaves, you can see, or even you can Google it also. Wikipedia, you can see that the relation between electron density and critical frequency, electron density or frequency, the refractive index. Refractive index, as here we have shown critical frequency, and similarly it is the refractive index also is proportional to 1 by n, square root of 1 by n. So you have this NME means the total number of electrons, maximum electrons in the E layer. NM, F1, total number of electrons or ions, charged particles in the F1 layer, F2 layer, okay? And half thickness is all. Now, as we know, the most of the ionosphere lie within the thermosphere. Thermosphere, as we have mentioned, in terms of temperature, we can say your spheres can be your troposphere, stratosphere, mesosphere, thermosphere, okay? So thermosphere is mostly the altitudes at which the temperature continues to increase. So at about, you get the minimum at about, in the mesosphere you get the minimum, and from there, the temperature will continuously rise. So here in the mesosphere, it is mostly heated by X-rays and UV from the sun, and those radiations also cause ionization and dissociation of atmospheric gases. So the neutrals get temperature because this ionizing strong ultraviolet radiation as well as X-rays hit them. So the neutrals become hot. That's why the region is hot. And also because these neutrals are hit by these strong radiations in the ultraviolet as well as in the X-ray region, they will also be ionized and dissociated. Dissociated means atoms N2 can be dissociated to N and N. Similarly, O2 can be dissociated to 2 oxygen atoms. So dissociation, ionization in terms of temperature increase, all this takes place within the mesosphere. And because it is closer to the sun, not to the surface below, so the temperature continuously increases. There is no process by which this temperature can come down. Okay. Now, here is a table. Here is a table where you can see these are say some values are given here. Ionizing potentials at different frequencies. You can see N2, this is ionizing limits, ionization limits. So N2 can have the solar radiation or the flux up to 79.6 nanometer. You can convert it to angstroms. So it will be 796 angstrom. O 911 nanometer or 911 angstrom. So H similarly like this, O2 1027 angstrom, like that. So this table is there. And now I'm coming down to F2 layer. So this is F1. This is F1 where you can get F1 and F2 20 to 911 ultraviolet. So this is the range. This is the range of solar radiations 200 to 911 angstrom. 200 to 911 to 91 nanometer wavelength. This is the range of radiations which ionizes the F1 and F2. Okay, this is the range of radiations which ionizes F1 and F2. Okay, now E layer comes down. E layer, you have radiations which are more than 91. That means 911. It is more than 911 angstrom, and it goes to 1027 angstrom. Ultraviolet, same ultraviolet range. If you just have a reference for your reference, if you have on your table the electromagnetic spectrum, you will see that from 20 to 1027, all these will be in the ultraviolet range. Ultraviolet, either extreme ultraviolet or EUV, all these will be here on XUV, EUV, ultraviolet. All this is from 20 to 1027. So E layer, you see, it is 91.1 to 107 nm UV, as well as your X-rays. X-rays below 20. X-rays below 20. So 1 to 20 nm X-rays ionizes all, important at solar maximum. So around solar maximum, not always, solar minimum, X-rays are mostly weak. So at solar maximum, your 1 to 20 nm X-rays, or you can say 10 to 200 angstrom X-rays. 10 to 200, it can be simply multiplied by 10, or you put a 0 here. 10 to 200 angstrom X-rays ionizes all. All means all the components, they can ionize this X-ray, along with this UV. Okay, D layer. What happens in the D layer? You have still harder X-rays, and that is from 0.1 to 1 nanometer. That means 10 angstrom to, 1 angstrom to 10 angstrom. Only within this range, very hard X-rays, ionizes all variable important if sun is disturbed. Normally during disturbed period, these hard X-rays are produced, and they can produce ionization in the D layer. Harder, Lyman alpha, 121.6 nanometer. Lyman alpha. All these radiations are related to some what is called now here it is Lyman alpha. Similarly, we have seen UV also. So Lyman alpha, what it does? It ionizes NO. Okay. And less than 118 to 111 to 8 nanometer UV also ionizes O2 at a metastable state. Okay. So in the D layer, in the E layer, in F1 and F2 processes are little simpler. It is only UV radiations dissociate as well as ionize. In the E layer, you have two processes, UV plus X-rays. X-ray also is a radiation only, but ultraviolet, and then it goes to the lower boundary, X-rays. D layer, you have different types of ionization process. One is hard X-rays, the other is Lyman alpha, the other is UV. So you see in the D layer, you have different ion spaces, and X-rays, Lyman alpha, and UV. All this can happen in the D layer. And C layer, it is termed as C layer. Normally people do not talk about this as C layer, but still it is cosmic rays, ionizes all but very small NE. Cosmic ray, you know, all these radiations, cosmic rays, particles only. So you have very small amount of ionization, but if your detector is very sensitive, then you can also measure some amount of ionization in the C layer also. That is why that graph is shown, that C and D. C is not that we do not have, we can have a C layer, but it will be very small amount of ionization. If it is 10 to the power 6 in F layer, it may be only 1 or 2, kind of, less than 10 in the C layer. Okay, so this is about how you get the different layers. As we have said, your initially, when I showed that curve in that figure 5 today, that if the solar radiations are strong, they will come down to lower heights in the atmosphere, and similarly ionize this. So UV, these are from 20 to 102 nanometer. They are strong, fine, but not as strong as this hard X-rays, or say particularly ionization UV greater than 111. That means in the higher range, this extreme ultraviolet. Less than 118. This is between this 1027 to 1118. So in that range. Therefore, different radiations with different strengths will come to different heights, and as a result, we get different amount of ionization, and also because the number of atoms and molecules vary with height, altitude. That is also one factor. That is also one factor why we get the negative ions in the lower atmosphere, why not in the upper atmosphere, upper ionosphere, because in the upper ionosphere you have only H or He. So it can be only H plus or Hc plus. You do not have a negative ion there. But lower below, you can have negative ions. So even in the E layer or D layer also, definitely. D layer, actually, you will get many negative ions. And D layer chemistry is very complicated. D layer chemistry, the production and loss process in D layer, I would like to tell you, the production and loss process of D layer was investigated by many, but Professor Mitra, an Indian, he was director of National Physical Laboratory, director of CSI also, and he was also the FRS in ionospheric physics, or can say atmospheric physics. So he proposed a D-layer ionization mechanism, and on the basis of that only he got this FRS. D-layer ionization mechanism. It is very complicated. You bring in all sorts of species. One species combines with another species, then recombination takes place, and then dissociation, etc., etc. It is a very complicated. You can see in some book. In some book, it should be available, but here we will be looking at only the species which we normally know. Normally know means this NO, then your O2, and then CO3, etc., etc. So here these words are given actually. So I think yes.
Next class
Yes. That is,
maybe
that is I have said 10:30 now, or 11:30. So I think if you do not mind, we will leave it here and continue discussion on the ionospheric layers, how they form, how they are formed. Now we know that these layers have different ionizing radiations, and also the density of your neutrals vary with altitude. Therefore, this combination of different neutrals as well as the different ionizing radiation source, you get the layers. So how it unfolds, we'll discuss tomorrow. Okay. Now for our students, I have already told Vinta that this whatever I am showing, I will take a print out, and I will specifically try to write, because these are available everywhere, means in any good book you will find. So I will try to write where to stress upon, where we should give stress while writing in the exam, or for knowledge purpose also, to keep us in a phrase, that means to know exactly what is happening. Alpha Chapman, beta Chapman, okay. That itself we know, but now why alpha Chapman, beta Chapman can have different variations, and whether it is exactly the ionosphere, what we see now, like that. So those small things I will write down, and then I will give it to you. Okay. So okay, for today, thank you.
Thank you, sir. Thank you very much. But that doesn't mean students, they do not need to write down whatever they understand during the class.
Yes.
Then the sir is going to provide
in the
material.
beginning itself, I have told them that they can have a rough notebook, and whatever equation is visible and is shown for a sufficiently long time, they can write, and then on their own they can try to see what is this? Why we are taking this ratio and like that. All are intelligent enough you can do. So,
Yes, sir. Thank you, sir.
thank you.